Okay, I'm doing the titration, a very quick titration of a weak acid with a strong base. I picked nice numbers so I could do this quickly. 30 milliliters of 0.1 molar HA, and I'm going to titrate it with 0.1 molar sodium hydroxide. The first thing you do, step one, is get the equivalence point. And you should be able to do this. It's 30 milliliters. Make sure you know how to do it. What's your units? Make it work. So 30 milliliters, so I do 0, 1/2 the equivalence point, and 5 milliliters past the equivalence point. It gives me these total volumes and concentrations, which I'll show you how to calculate in a second, and these pHs, and we'll show you how to do these. Okay, so here we go. The first step is 0 milliliters. So with 0 milliliters right here, I have no strong base, so that's just a weak acid. So my ice table is 0.1-00 minus X, X, and X, 0.1 minus X, dash X and X, and I get Ka equal X squared over 0.1 minus X. You should be able to solve this. X equals 3.16 times 10 to the minus 5th. Very straightforward. By the way, right here I have picked out very nice Kas for this problem so we can do it quickly. Okay, these are given, or you would look them up for a particular acid. All right, now that's first step. Second step is 15 milliliters, so that's when I write this reaction. That was 0 milliliters, 15 milliliters. I like to label these and I forget all the time. And I'm reacting it with sodium hydroxide, NaOH. There's the reaction, I just wrote it. I've got HA plus sodium hydroxide, one-way arrow. 3 millimoles, that's coming from the 30 and 0.1, and 1.5 milliliters because I am doing 15 milliliters of 0.1 molar sodium hydroxide. So when I'm done, I get 1.5 here, 0, 1.5, 1.5. We recognize that as a buffer. I have weak acid and weak base, substantial amounts, so I use Henderson-Hasselbalch, pH equal pKa, plus the log of the base over the acid, and that will equal 8 plus the log of 1.5 millimoles over 1.5 millimoles, which the log of 1 is 0, so I get 8. And that's where I get this number right up here in this slot in the right corner. Okay? Very straightforward. Next step is to do 30 milliliters. And again, these are all in millimoles, so I have 3 millimoles. Make sure you know how to do it. 3 millimoles. Didn't put my units in last time, but tough. Figured out 0.03 millimoles and 3 millimoles. I recognize this as a weak base because all I have left in solution is weak base. So that is a Kb problem, so I set that up. Kb is equal to, whoops, got to do my ice table, A minus plus H2O yields equilibrium, HA plus OH minus, and initial change equilibrium. I need the concentration. I can get it 0.3 millimoles divided by the total volume, which is 60 milliliters, because it's the 30 milliliter slot right there. Okay, so that gives me 0.05 dash 00 minus X, X and X, 0.05 minus X, dash X and X, and I get Kb is equal to X squared over 0.05 minus X. This is freshman chemistry, That implies that X is equal to 2.23 times 10 to the minus 4th. That's my number right here, and in this right-hand corner, and that gives me a pH at 10.35. Remember, these points down here are OH minus. That's what I'm solving for in here, OH minus for these two. Okay? People get mixed up there. I'll do 35 milliliters down here a little bit. Initial final 3 millimoles, 3.5, 0, 0, 0.5, 3, and 3. In this case, I have a strong base left, and that's all that I have to worry about. Strong base here. That's the sodium hydroxide up here at the reaction. So my concentration of strong base is going to be 0.5 millimoles of hydroxide divided by the total volume, which if you look at your table is 65 milliliters, and that gives me a concentration of 7.69 times 10 to the minus 3rd molar. And so my table is complete. That is my value right here. Okay, and that gives me a pH of 11.89 over here. Copy all that down, and I'm going to move things. Okay, I've moved my table down here, and I have my graph axes. Again, you'll get graph paper. So I'm ready to plot. At 0, I have a pH of 1, 2, 3, 4.5 right here on the axes. And the next volume is 15 right there, and that is a pH of 8. Looks a little bit different, but you'll notice in a second that it's going to be pretty much the same. At 30, I get 10.35. Not caring too much about where I put these. This is just an estimate. And at 35, I have 11.8, almost 12. So my curve, now you're going to want to do this. I'll draw it real light. You're going to want to do something like that. Do not put a straight line in there. I'm going to undo that. Okay, oops, I undid a little bit too much. 35 is about 12. Okay, so the easiest way to do it, and I'll do it again with the straight line, is do a step ladder. Up, over, up, and over. Now, I don't want that because that's not how it looks. Draw a curve. You can exaggerate it. It's not going to curve as much. If you have your template down, you'll note that. Okay? That's the kind of curve you want to draw. Okay? That will give you most of the points. Now, you got to identify the buffer region. The buffer region is pH equal pKa plus or minus 1. And so that buffer region will go pKa is 8, so it'll go from 7 to 9. So if I come up here at 9, that's right about here. You don't have to be real good at this. And 7's right about here. There's my buffer range right along that curve from there to there. Okay? That's the buffer range. I want that identified. So that's the buffer range. You circle it. Doesn't have to be good, but it's got to be reasonable. I don't want a little circle like that. I want it out here. I don't want it way over here on these points either, so be careful with it. This is the best buffer. Right at 1-to-1 ratio. And you've got to label the equivalence point. Equivalence point is right here. This is completely weak acid, and this is strong base. Okay, that's it in a nutshell. Good luck with that on the exam. I will always ask you to do 0, half the equivalence point, and 5 milliliters after the equivalence point.